All right, everyone. Thank you very much for joining us for this SNAPP seminar. It's my pleasure to introduce Enlu Zhou, who's also a colleague of mine at Georgia Tech, for this talk. Enlu is a Fouts Family Professor in ISYE at Georgia Tech. She has varied interests across applied probability, simulation, stochastic optimization. And she's won several awards. Maybe I'll mention a couple from her bio, including an AFOSR Young Investigator, an NSF Career, and an Outstanding Simulation Publication Award. So she happens to be president of the Simulation Society at Informs also from 24 to 26. So without further ado, I'm going to hand it over to Enlu, who's going to tell us today about understanding two machine learning algorithms through the lens of continuous time approximation. Enlu, the floor is yours.
Okay, thank you, Ashwin, very much for your nice introduction. Good morning, everyone. First, I would like to thank the organizers for organizing this SNAPP seminar series since pandemic. It's been a very nice seminar, and I'm very happy to be invited and speak here. So today, I will discuss how to understand some machine learning algorithms through the lens of continuous time approximation. So this perspective can help us to analyze convergence properties and to understand the empirical performance of these algorithms. Oops. Okay, so just as an overall background, as we all know, reinforcement learning, especially when incorporating deep neural networks, have achieved many empirical success in applications. So despite of this empirical success, there's usually a lack of theoretical understanding or justification of these algorithms. So this motivates us to look at some of these algorithms. And in this talk, I will focus on two algorithms. The first is the natural policy gradient, NPG, with reuse of historical trajectories. So NPG is an important reinforcement learning algorithm. And in practice, people often reuse the historical trajectories of older policies in order to improve the computational efficiency of NPG. But the theoretical advantage of reusing historical trajectories has not been studied until our recent work. So in RL, just this picture illustrates RL in a very high level. So a learning agent iteratively interacts with the environment by taking actions and then receiving rewards and observations. This iterative interaction may eventually lead to an optimal policy, hopefully. So RL algorithms can be roughly categorized as value-based methods and policy-based methods. In value-based methods, they are mostly rooted on the Bellman equations. So the goal is try to learn the optimal value functions through iterations. And then the policy is induced from the value functions. And policy-based methods are sort of a more direct way to learn the policy. The idea is just try to optimize the policy, usually based on some gradient-based methods. So NPG falls into this category. And other well-known policy-based methods include proximal policy optimization, PPO, and trust region policy optimization, TRPO. First, for the setup, so the underlying model for the RL here we consider is infinite horizon discounted MDP. So it's characterized by S, the state space, the A, the action space, the transition models. So this is a transition probability from the current state action pair STAT to the next state ST+1. And R is the reward function on the state action pair STAT. Gamma is a constant between 0 and 1, which is the discount factor that discounts the future rewards. And rho 0 denotes the distribution of the initial state. So the goal for the agent is to maximize this expected total discounted reward. And here we consider a policy a randomized policy that is parameterized by theta. So the policy basically maps a state to a distribution over the action space. So this maximization problem then reduces to the maximization over the parameter space, which is a finite dimensional space. So we denote this total reward as eta. So we try to maximize eta over theta. So to do the policy gradient or to maximize this total reward, it is natural to derive a gradient, right? A gradient of the reward with respect to theta. And it is well known the policy gradient take this form. Here I just want to point out an important notation here, which is the d super pi theta. So this denotes the discounted occupancy measure defined in this way. So the discounted occupancy measure can be understood as the long run proportion of time spent in the state action pair S and A. And with this policy gradient, then we can update the policy parameter by basically this is the steepest ascent algorithm. And here alpha n is the step size, and this projection operator basically projects the iterate back to the feasible region of the theta. However, the policy gradient method, the policy gradient is sensitive parameterization of the policy. If we reparameterize the same policy in a different way, then the gradient may be different, and then the update will be also different. So this is not very nice. So to address this issue, natural policy gradient was proposed. The idea is to find the steepest ascent direction in the distribution, or in other words, in the policy pi of theta. So if you compare the natural policy gradient method with the policy gradient method, the only difference here is Fisher. There's an inverse of the Fisher information matrix term here. The Fisher information basically captures the geometry of the policy space or the distribution space. So it leads to the invariance. So that this update or this Fisher information, this gradient here, the natural policy gradient term is invariant to the reparameterization of the policy. So this is the ideal algorithm, but both the Fisher information and the policy gradient terms, they involve expectation, right? So they involve expectation with respect to the discounted occupancy measure. So in practice, to implement that, they need to be replaced by some estimates. So just abstractly, I will use the notation tilde here to denote some the sample estimate of those two terms. So a naive way to estimate these two terms is just to do sample average, right? So we can draw samples, basically draw samples from the occupancy measure, this d super pi theta n. And this usually requires to run the policy for a long time, and then take the pairs, the state action pairs we observed from the trajectory as the samples. So you can imagine that can be costly because we need to run the policy for a long time. And then the vanilla natural policy gradient basically use this mini batch sample estimators. Basically, we just take a small sample size B and then take the average sample average of these samples as the estimator for these two terms. So when we use a small batch size, these estimators usually have a large variance, right? And if we want to reduce the variance, then we have to increase the batch size B. That can be costly because the samples are costly to sample, and also sometimes these terms can be expensive to evaluate. So how can we sort of, try to reduce the variance, but also try to kind of maintain a small or inexpensive cost here? So a popular method used in practice is to use off-policy evaluation via importance sampling. So the idea is that the policy here, these two terms are not evaluated on the current policy theta n, but they are evaluated on some older policies, maybe like the previous iterations, and use the past evaluations or past trajectories of the older policies, and then by a change of measure, a change of probability measure, we can convert these evaluations to be the samples under the current policy. So to be specific, I think a lot of people here might be very familiar with importance sampling, but just to kind of refresh your memory here, so we can rewrite the expectation under the probability measure pi theta prime. Now rewrite that as the probability expectation under the probability measure pi theta, and that will introduce this likelihood ratio term, which is the ratio between the probability, the occupancy measure under pi theta prime, and the occupancy measure under the reference distribution pi theta. So we denote this likelihood ratio as W. And then with this, then we can use, now think about theta. Theta prime is our current policy, and theta is some older policy. And then we can reuse the samples from or evaluations from the previous iterations under the different theta n's. We just need to weight those samples by this likelihood ratio. And here we use K1 iterations. That includes the current iteration. So basically reuse the past K1 minus 1 iterations. And each iteration, there are B samples. And for estimating the Fisher information term, we use K2 iterations. So these are the new sample or the new estimators for these two terms by reusing the past samples or past trajectories. So just to recap, this is the algorithm. By the way, the algorithm is not new, it's not our contribution, but I'm just introducing the algorithm here so that we can see how we can analyze this. Okay, so the first is the initialization phase, and then during the iteration, we first update this policy parameter according to the natural policy gradient method. And here, these two terms are computed using this estimators. And then the second step is to draw those ID samples from the occupancy measure by interacting with the environment. So this is the expensive step. That's why we try to keep this size B to be small. And then we just do this iteratively until some stopping criterion are satisfied. And then we can output this policy parameter theta n and the corresponding policy. So the algorithm is pretty simple. Now the questions that we want to study is that whether this reusing past iterations or past samples will help. So basically, these questions basically concern about the qualities of these two estimators, right? Estimators of the Fisher information and the policy gradient. So very naturally, we would want to ask these questions, right? If this estimator, this RMPG estimators are unbiased, are they unbiased? Okay. Unfortunately, sorry, I just recovered from the flu, so I still cough a lot. Hopefully it's bearable. Okay. So unfortunately, so these estimators are not unbiased. That is because these iterations are correlated, right? So the theta n's are correlated through the iterations, and then these samples drawn based on theta n, they are also correlated. So this correlation introduces bias. Okay, so this is not a good news. And now, how about the variance, right? As I mentioned, the motivation of using the by reusing the past samples is try to reduce the variance of these estimators when we still use a small batch size for each iteration. So do we expect these estimators have less variance than the vanilla estimators? Well, unfortunately, the answer is still not definitively yes or no. It depends on the form of the objective function and the likelihood ratios. So this is actually also well known for importance sampling. It does not always reduce the variance. Okay, so now we have these bad news, right? So if the estimators are not unbiased, and also it's not necessarily have less variance, so then what's the advantage of reusing the past samples, right? Why does that perform well in practice? So that is the question we are curious about. And then we use the analysis. Later I will show you very soon that we can say that this RMPG converges. First, it converges to the same solution as the VMPG, the vanilla algorithm, without reusing. But still, that does not answer the question whether reusing samples is better. So our further analysis shows that the answer is yes. Reusing samples gives us a faster asymptotic convergence rate. Okay, so now I will focus on the last two questions. Okay, so first about the asymptotic convergence. So does the convergence, does RMPG converge? Yes, the answer is yes to the same solution as the VMPG. So let's recall this is the RMPG iteration. And here we look at some, we kind of change the iterate or the simplify this iteration a little bit by for the feature information, we just use the current samples. We do not reuse, because if we reuse, that complicates the analysis a lot. And also our numerical experiments shows that whether we're reusing or not reusing samples for the feature information actually matters much less than here for the policy gradient. So we only have reusing samples here for the policy gradient. And also we add this small term epsilon times identity matrix ID. This small positive definite matrix makes sure the feature information matrix is strictly invertible. Okay, so the challenge in the analysis here is again the correlation in these gradient estimators because of the reusing. And our solution here, we relies on this ODE method proposed by Cushing and Yin, but we have to do a little bit innovation here, is that we have to explore the hidden Markov property of the effective memory. So basically we have to augment sort of the state, and then that will give us some hidden Markov reveals the hidden Markov property, and then we can apply a fixed chain state chain method to prove this. Okay, so here are the main assumptions. I don't want to bore everybody with the technical details. Let me just briefly say these assumptions are generally mild and justifiable. So as my title of my talk shows, it's based on the continuous approximation. So basically, we will approximate the discrete iterate theta n by a continuous stochastic process on theta of t. And that can be done just, by this linear sort of piecewise constant approximation. And then we can show that the discrete time iterate theta n will converge to this continuous time process. And then this continuous time process satisfies this following ODE, ordinary differential equation. So as we know that for an ODE, its trajectory is going to converge to an equilibrium point that makes basically this derivative to be dead zero, right? So then this iterate theta n will eventually converge to an equilibrium point that makes this ODE, this derivative, to be 0. Okay, so this derivative becomes 0. By the way, the z here is the extra term due to the projection. And in the limit, usually we don't have this projection term. So basically in the limit, when this derivative becomes 0, that means this term becomes 0. Okay, right? So because the inverse Fisher matrix here is positive definite, so that basically implies this policy gradient will be 0 at the equilibrium point. So basically, from this theorem, we can see that if there's no local minimum on the boundary, then this term, okay, this policy gradient term will converge to 0 with probability 1 as n goes to infinity. So that implies that the theta n, the policy parameter theta n, will converge to a stationary point or a local minimum or a local optimum of the policy gradient, right? That makes the policy gradient to be 0. So this is exactly the same convergence or the same ODE that for the vanilla policy gradient or the vanilla natural policy gradient will observe. So this theorem basically implies reusing samples in NPG will converge to the same solution as the vanilla NPG. Okay, now so the second question is, right, whether reusing samples is better. So yes, basically, we will show that through also the continuous time approximation. So here we need some extra assumptions. Again, these assumptions can be justified. They are just a little bit more strict than for the asymptotic convergence. Okay, so here the approach is to look at this process. Okay, so this process is basically we look at the difference between theta n and the limiting point theta bar scaled by the square root of the step size alpha n. So this is like the scaled noise. Okay, so we look at this scaled noise process, and that follows an SDE. I didn't put the express form of the SDE here, but then for that SDE, we can derive its solution. So by deriving its solution, we can show this asymptotic normality result. Basically, this the normalized noise process will converge weakly to this limiting normal distribution as n goes to infinity. And this is just like, the central limit theorem, right? So the asymptotic convergence rate is determined by this square root of alpha n, as well as the magnitude of this limiting covariance matrix, sigma infinity. And if we look at this sigma infinity here, we actually will notice it has this 1 over k term here. So if we compare with the vanilla NPG, we will notice this is the extra term. So basically, it reduces this covariance term by a factor of 1 over k. Okay, so this implies that the asymptotic convergence rate of theta n to its limiting point is of this order, and this order basically implies that the asymptotic convergence rate decreases in this reuse size k. K is basically the number of iterations or the number of iterations that we reuse the sample size. This kind of is intuitive. This result is intuitive because it's basically shows that we increase the sample size by k times by reusing this. So the corresponding covariance is reduced by k times. But we also notice there's another extra term here, which is not reduced by k. So this is this constant term here. So this shows that the reusing, although the reusing is helpful, but it has a diminishing marginal effect, because as k increases, this term will be dominated by this constant term, so it will no longer be very effective. Okay, so next we show some, we did some numerical experiments to sort of, to kind of verify our theoretical insights here. So here we consider this cart pole example. There are 4 states, position of the cart, velocity of the cart, angle of the pole, and velocity of the pole. The actions are push the car left or right. And the goal here is to balance the pole on the moving cart. So here we can see that this green curve is the vanilla MPG, and the 3 other curves are RMPG with different reuse size. So we can see that this is the average reward over like 100 macro replications. So we can see first by reusing the samples, the reward does converge faster than the VMPG. And we also notice when we increase the reuse size from 10 to 50, then to 100, there's a little bit increase in the convergence rate, but it's not very obvious. So that again verifies that the increase in K has a diminishing marginal effect. And then this picture is actually quite interesting. We look at the standard error across the different macro replications. And then we can see this green curve, the VMPG has the highest standard error across those different macro replications. And the other ones, when we reuse the samples, they have less standard error. So this basically implies reusing the samples also helps to reduce the variance of the iterates, and that helps it to improve the stability of the algorithms when we run the algorithms, for different runs. And we also test this reusing on the proximal policy optimization, and we also have the similar observation here. Okay, so so this is the first algorithm. Now let me talk about the second algorithm here. The second algorithm is momentum stochastic gradient descent, MSGD. So this algorithm has also been introduced for a long time. It has been well studied for convex optimization, but it's not it hasn't been studied so much for non-convex optimization until our paper. So here we'll consider a general non-convex optimization problem. So the objective function is the expectation of fx Kc. X is a decision variable, Kc is the random vector. And we assume in this non-convex optimization problems, we only have isolated local optima and strict saddle points. Basically, the local optima x star satisfy this condition, and then the saddle points x hat satisfy this condition. And then the momentum SGD, sometimes also called the heavy ball approach, heavy ball SGD, has this iteration. So we basically has the usual stochastic gradient descent term here. Eta is the step size. Here we consider a constant step size. And then this is the stochastic gradient of the objective function. And we also have the momentum term here. And here mu is the momentum parameter, which is constant between 0 and 1. So we would like to see basically how does the momentum help, right? Does the momentum accelerate the convergence? So based on our analysis, the short answer is yes, the momentum initially accelerates the convergence, but it actually hurts the convergence when xk is when the iterate gets close to a local optimum. The second question, because it's there might be a lot of saddle points, right? So we hope that our algorithm can escape from the saddle points and converges to a local minimum. So our analysis shows Yes. So the answer is yes. The momentum helps or accelerates the escape from saddle points. So these are the short answers. Now let me get to the long answers. Okay. So first is about the global convergence, or the asymptotic. I mean global, not in terms of the not doesn't mean, maybe I should not say global, but doesn't mean convergence to a global optimal. Just means the global behavior of the algorithm. So again, we use the continuous approximation. We approximate the x eta, x super eta is the iterate here, where by a continuous time process. So we can show that as the step size eta goes to 0, this discrete time iterate x eta converges weakly to the continuous time process x, and this continuous time process x satisfy this ODE. Okay, this ODE. So again, the limiting point or equilibrium point of the ODE is a point that makes this gradient term to be 0. So this shows that this continuous, this xt process can converges to an equilibrium point or a stationary point of the problem. And also compare with the vanilla SGD without the momentum. Okay, so basically that's this term, if this term is gone, then that's the vanilla SGD. When we compare with that with vanilla SGD, vanilla SGD also satisfies an ODE without this term 1 over 1 minus mu. So compare with these two ODEs, we can say that asymptotically, MSGD is 1 over 1 minus mu times faster than the vanilla SGD in convergence to the neighborhood of a stationary point, given the same initialization. Okay, and notice mu is a constant between 0 and 1, right? So this 1 over 1 minus mu is a constant bigger than 1, so it's faster. And now let's look at the local behavior of the algorithm. We are mostly concerned about the saddle points. We don't want to be trapped at the saddle points. So to analyze this local behavior, we use this SDE approximation. So again, we define this normalized process, just like in the previous for the first algorithm. We also define this normalized noise process. And this is normalized by square root of the constant of the step size eta, and then its continuous approximation converges weakly to the unique stationary point of this SDE. So if you are very familiar, you're an expert in SDE, you will notice this is the OU process. Okay, and basically we can solve this SDE analytically and get its solution. So by doing this, I basically left out a lot of the theoretical results here. But basically, starting from this theorem, we have some lemmas to imply that the momentum SGD accelerates escaping from saddle points by a factor of 1 over 1 minus mu, or by 1 minus mu times. But it hurts the final convergence around the local optimal due to this increased variance. So this momentum is a double-edged sword. It helps the escaping from the saddle points, but it also kind of hurts the convergence to the local minimum. Okay, yeah. So overall, when we put these results together, we can say the MSGD, the overall behavior of the momentum SGD on a non-convex optimization problem can be roughly considered as going through these 3 phases. So the phase 1 is when it's around the saddle point, the momentum enlarges variance. So it encourages exploitation and helps escape from the saddle point. And in phase 2, it traverses between the stationary points. And here the drift of this SDE actually will dominate the variance during this phase. So the traverse will more or less become a deterministic trajectory. And then in phase 3, when it is around a local optimum, the momentum again enlarges the variance, just like when it's around the saddle point. So it hurts the convergence to the optimal. So what can we do? We propose a remedy is to anneal the step size, basically to decrease the step size gradually to 0. So that will helps the convergence. So here are some numerical results. We first look at a simple problem of streaming PCA principal component analysis. So we applied MSGD as well as the vanilla SGD to this problem. The first figure here is for the vanilla SGD. So you can see it goes through these 3 phases. Phase 1 is to escape a saddle point and then traverse between saddle points, and then eventually it converges to the local optimum. And then this plot, the second plot, the plot B here, is for the momentum SGD. And if you compare momentum SGD with the vanilla SGD, you will notice the first 2 phases are very fast. Okay, we can barely recognize the first 2 phases. That is because of the momentum. The momentum greatly accelerates the first 2 phases. Okay, and then it gets to a 3rd phase, but then it just keeps oscillating around the local minimum. It fails to converge. Okay, so then we apply the annealing of the step size here, starting from here, and then after we apply the annealing, the momentum SGD also converges to the local optimal. Okay, and here is the I think here is the this is the optimality gap, or the error. And we can see that basically compare these algorithms, then MSGD, momentum SGD, converges much faster, and also it converges to a local optimum after we apply this the step size annealing. And then we also compare these algorithms, vanilla SGD and MSGD, on training deep neural networks. Again, our algorithm shows that the best MSGD significantly outperforms the best vanilla SGD. So just to conclude, so the continuous time approximation of algorithm iterates is a very powerful analysis tool. So it can basically, view the algorithm iterates, the discrete iterates can be viewed as like a noisy discretization of some ODE or SDE. And then, with those tools from ODE and SDE, we can analyze their asymptotic convergence and asymptotic convergence rate. And another powerful tool, which I didn't show in this talk, is basically like the Lyapunov approach, which helps us to analyze the stability of an equilibrium point of an ODE. So this tool from like the control theory. So this Lyapunov function, this kind of analysis tool from control theory, can be used here for us to analyze the behaviors of algorithm iterates. I think that's the main message. I think basically, the continuous time approximation should be used a lot when we try to analyze those discrete time algorithm iterates. And here I just demonstrate that in 2 algorithms. And for the NPG, the natural policy gradient algorithm, using our analysis, we show that reuse the historical trajectories helps to accelerate the convergence. And for the momentum SGD, we show that momentum helps to escape from saddle points in non-convex optimization, but it hurts the final convergence, which can be easily remedied using an annealed step size. Okay, so these are the 2 papers. for this talk. So thank you very much. Thank you for, joining the talk even during Thanksgiving break. And I think I finished pretty early. So yeah, if you have any questions, please feel free to ask.
Thank you, Enlu. Yeah, if there are any questions, please feel free to unmute yourself and ask. If you feel like you don't want to unmute yourself and ask, you can put them in the chat and I can ask them on your behalf. So I'll maybe start with a couple of questions.
Okay.
So the first part of your talk assumed that the minimum is inside my constraint set, right?
Yeah.
So essentially you have like a full dimensional Hessian no matter where or whatever. So at some level, you're in the interior of the constraint set, and then everything is asymptotic. So you get these convergence theorems that depend on the inverse of a Hessian. But what if my optimum is actually on the boundary of my constraint set? Do you actually still recover kind of like the tangent normal type results, or is it just not something that you cover?
Well, it will be the same, basically. So if the minimum is on the boundary, then we just have this extra term z here, which is the projection term, the force that projects the iterates back to the boundary. And we will have the same projection term for the ODE corresponding to the basically the vanilla natural policy gradient. So in terms of the asymptotic convergence behavior, reusing and not reusing, they still have the same thing. Yeah, they will still converge to this. Yeah, I just say, it's just easier when I explain when it's not on the boundary, we can see this gradient term will converge to 0. Yeah.
I have another maybe technical question, but you had an assumption on your occupancy measure stuff. Was that for basically just at initialization, or was that throughout the?
Yeah, that's a great question. Yeah, so yeah, good catch. So this occupancy measure we needed to bound away from 0 throughout.
Oh, for all
Right,
theta.
right,
Oh,
right,
I see.
right. So this is probably the strongest assumption we have. Yeah. So if it's not bounded away from 0, I remember like in our analysis we will run into some technical issue.
Yeah,
So
I
we
mean
need
these importance ratios. I mean the likelihood ratios are going to blow up and stuff.
Exactly. Right? Yeah, it will blow up. Yeah.
I see. So there's been all this work. I mean, I'm just curious. There's been a bunch of recent work. I mean, more in non-asymptopia, where you can actually track what's going on with the iterates about some sort of implicit regularization behavior where there's automatic exploration, in that you don't have to assume this condition in principle. You can just assume it at the initializer and then inductively show that it continues to hold as the algorithm progresses. Do you expect that something like that is true here?
Oh, that's a very good point. Yeah, I think, if you initialize that to be sort of non-degenerative, and if your algorithm keeps in like a constant exploration, maybe like an epsilon greedy kind of exploration, you can automatically maintain this assumption throughout the iteration. I think that's a very good point. So that maybe can be incorporated. Yeah. Thank you.
Yeah, of course. Any other questions from folks? So maybe I have two related questions.
Okay.
Sorry.
Yes.
I'm the host. I've been assigned question duty.
Yeah.
So a lot of this is based on, well, there are two aspects of this. I suppose there are two asymptotics, right? There's the continuous time approximation. And then eventually we're talking about asymptotic variance. So there's two senses in which, a theory like this could be made non-asymptotic. So maybe just a broad question. Can you comment on, like, I understand that, especially in the second part of the talk, you had all these qualitative conclusions about, different phases that the algorithm is in, et cetera, et cetera. But non-asymptotically, at some level, we want to be able to recognize which phase you're in.
Yeah.
So that you can do what it is that's optimal for that phase. is there guidance like that that can come from continuous time, or is it really you just have to go and do it in discrete time?
Okay. That's yeah. So yeah, so we have thought about the non-asymptotic analysis. So right now it seems like, these are the asymptotic analysis and non-asymptotic analysis basically like take very different approaches, like completely two different machineries. um, so um, so whether we can, using this kind of ODE SD approach, whether we can recognize the sort of the non-asymptotic behaviors, actually, I'm not sure. So I think that's a very tough question. I think one question is basically, one thing is probably, is there anything we can like borrow from the control theories, right? So basically, these are initiated from like control theories, looking at stability of like a nonlinear systems. So whether we can borrow something from the control theory to study sort of the non-asymptotic behaviors. Yeah, and also one limitation here is that, we have this discrete iterate, we have the continuous trajectory, right? They have a gap, and their gap only like close to zero, right? When t goes to infinity. So if we look at some finite time, we also need to first characterize this gap, right? And then, you have like two things, right? The first is the gap, and then you have also the gap of the trajectory to its equilibrium point. So I feel like using maybe this type of machinery, it's not very natural or easy to look at the non-asymptotic behavior. Yeah, but it's very challenging to look at the
Oh, I
non-asymptotic
completely
behaviors.
agree. Just
Yeah.
to be clear, that was not a criticism. It was just, when a lot of ODE approaches, classically, right, like the whole ball or mind stuff, even for just general essay, they sort of you have to be very, very careful to taking them to discrete time. And sometimes even the qualitative conclusions change from continuous
Right.
time to
Yeah.
discrete time. So
And
I was
and
just
also
curious about whether you had some idea of how some of your qualitative conclusions, whether they're sensitive to this discretization versus continuous, or whether
yes.
they're just robust to.
Yeah. So that actually is something I want to mention, is that the discretization also matters
Yeah.
sometimes. Yeah. So basically, you can go from the other perspective. You design some ODE that converges, and then you discretize your ODE to get your algorithm. And different types of discretization can lead to different, convergence rates. So that is also another kind of a branch of study, like sort of in this kind of realm.
Indeed. Okay, we have 3 guests. I'm going to open the floor again to any questions. We'll wait another 30 seconds. If there are any other questions.
I actually had a question, but I think you already asked for me. So it relates to if Euler approximation, like for example, the accuracy, the fidelity it does to, recover the trajectory of the gradients. Um, so um, so to my mind, I think Euler approximation is also discretization of the,
Right.
continuous um, process. So so intuitively, what kind of additional information we could get from this kind of modeling gradients as ODEs? So that was actually my question.
Okay, yeah, very good question. Yes. So if you're starting with an ODE and you want to do an Euler discretization, right? So you can get a discrete iterate. And that's actually most of the algorithms here can be viewed as an Euler discretization of the corresponding ODE. And there are also some studies before they use a higher order discretization. For example, they use like a Runge encoder. I could not really pronounce it, sorry, but like a higher order discretization of ODE. Yeah. So, and they show that by controlling this discretization carefully, you achieve like a faster convergence. Yeah.
Okay, got it. Thank you so much.
Yeah. Thank you.
Any other questions? All right. If not, let's thank Enlu very much. Yeah, someone's thanking you at the chat as well. So thank you very much for the talk, Enlu, and yeah, thank you for giving the seminar. The recording will be up on our website shortly.
Okay. Yeah.
Thanks
Thank you very
everyone for
much.
joining.
Thank you, everyone. I wish you a happy Thanksgiving break.
Thank you.
Thank you.
Okay. Okay. Bye bye.